Welcome to this discussion of the textbook chapter, Why Buildings Fall Down, Chapter 1, The First Structural Failure. Early in the chapter, the authors talk about forces in buildings undergoing shaking from an earthquake. And we'll look at seismic loading in buildings in some detail in this course, but one of the statements they make is that the forces developed in the building from an earthquake are directly proportional to the mass of the building and proportional to the square of the height of the building. And I wanted to address why that was, because that's actually asked in the reading guide. So here we see a building that has been damaged by an earthquake, and this is kind of classical earthquake damage for a building. You'll notice that the highest structures are nearly completely undamaged, while the base structure is completely destroyed. The first story is completely destroyed. The second story is heavily damaged here. The third story is moderately damaged, and then less and less damage as we go up. Well, this is logical, because if you think about this type of an event, let's draw this building in a very simple sectional, or elevation view. Here's the building, and it's anchored to the ground. Now, the damaging wave in an earthquake is this transverse wave. It's this shaking of the ground back and forth, left and right, you can think of it as. Well, this building has some amount of mass, and one of the cool things we can do is that we can consider all of this mass of this building to be at this point that we call the center of gravity, which is, for a building of uniform section like this, likely in the middle of the floor plan, halfway up. Well, now let's think about each individual floor. So let's see how many floors we have here. It looks like 1, 2, 3, 4, 5, 6 stories. Let's break this building into 6 stories. First floor, second floor, third floor, fourth floor, fifth floor, sixth floor. As the ground is shaking back and forth, I want you to think about how much inertia is above this top floor plane. Well, 5/6 of the building's mass is above this plane. So what that means is that these first floor walls are undergoing severe shear forces, and maybe it's good to just talk a little bit of basic physics. You recall that Newton was a very brilliant human being, and he came up with 3 laws, and his second law said that force equals mass times acceleration. Now remember that acceleration is just change in velocity. So when this building is shaking, when the ground is shaking back and forth, the building is being accelerated. And the force that's being developed is directly proportional to the mass. So think about the walls on this first floor. These walls are attempting to resist the force developed, or develop the force to accelerate 5/6 of the mass of the building. How about the walls on the second floor? How much of the building's mass is above the top of the second floor? Well, it turns out it's 4/6, or 2/3. How about the third? Well, it turns out that only half of the building's mass is above the third floor. In the fourth floor, only 1/3 of the mass. In the fifth floor, only 1/6 of the mass. And after the top of the sixth floor, there is no mass above that location. This explains the severe damage to the lowest floors of the structure. The other thing that plays into this somewhat is that these first floors, which are somewhat flexible, attenuate the shaking of the earth. And the word attenuation, there are a couple of words that get used in engineering that are worth knowing about. There's attenuation, which might be a new word for you, and there's attenuation. And attenuation might be somewhat familiar to you because you're probably familiar with the word antenna. And so if you think about attenuation, it's basically the act of accentuating a signal. Oops. Right? The purpose of an antenna is to help that radio signal get out of the transmitter or get into the receiver. Whereas Attenuation is kind of trying to cancel a signal. Now, an application of this concept that's valuable for the fire service is probably crash attenuation. So I'll cue a video here where we can watch a crash attenuator at work, and you'll get a concept of what the word means. So what you're going to see here is a video of a crash attenuator. And basically what you can see here in this video is that it's a structure that gets mounted to the back of a motor carrier truck for highway use, and it provides basically some energy absorbing material so that this car that's going to crash into the back of this crashes and stops. I would not be surprised to see a device like this on fire apparatus in the near future. These are manufactured for highway maintenance vehicles. You see them on the backs of dump trucks and things of that nature, and it is likely just a matter of time before this makes it into the fire service. So you can see it attenuates the crash. It damps the energy of the car that is crashing into it. So the story is that these first several stories of this building are somewhat flexible, and they play some role in attenuating the oscillations of the ground with the earthquake. So that helps. Now, why should these forces be proportional to the mass? Well, because Newton's second law says that the forces developed in the first floor will be proportional to the mass of the building. Why then the square of the height of the building? That maybe is not quite so intuitive. But think about this. If the building has some height, there is some amount of mass in the building associated with that. And if the building is uniform in section and we double its height, what will happen to its mass? Its mass will double. The other thing, though, is that if we double its height, the distance of the center of gravity from the ground will double. And this matters because when we shake this building, we don't simply develop left and right forces. We don't simply develop these transverse forces. We also develop moments. And we'll talk a lot in this course about moments and calculating moments. But a moment is a twisting action that makes this building want to pivot about its base left and right. And that moment depends both on the force that's developed at the center of gravity and the distance of the center of gravity from the ground. So if we double the height, not only is the mass twice as large, but the distance to the center of gravity is twice as large. And so any change in height, basically a doubling of the height represents a multiplication by a factor of 4 of the force. So force is proportionate to mass times the height of the center of gravity squared for this type of structure. And that's what the author was getting at when they talked about seismic forces in buildings. This is figure 1.1 from the textbook. It's the Pyramid of Mightum, and it's one of the oldest remaining structures from antiquity. And the authors in this section of the book are talking about tall structures. This was about the limit to tall structures in the time that the pyramids were built, because the building material was stone, which if we think about a good building material, there are certain characteristics that are essential to building materials. One is what we might call the strength of the building material, and typically we would express this in the number of pounds per square inch of stress the material could withstand. And we'll talk about that in some detail later in the course. Another characteristic that's important for building materials is their weight in pounds. And it turns out that how tall you can build a structure is really just a factor of the ratio of strength to weight. In fact, we would call it the strength to weight ratio. So the maximum height, if we think about the maximum height of a structure, is proportional to this ratio. What that meant was that when the only available building material was quarried limestone, that's a relatively heavy, relatively weak material, you had to build very conservative structures like this pyramid. It really wasn't until lighter weight building materials, namely steel, came along that we were able to build tall buildings. So as you notice in the diagram, much of the external sheathing rock of this pyramid has fallen off to its base. This pyramid was constructed with a 52-degree side angle. And this behavior is something that we're going to see over and over again in the construction industry, that this angle, the slope of things that are loosely piled, really matters. Basically, the story is that if you started this pyramid with a block of some weight, well, then think about the blocks kind of below it. The blocks below have to support not only their own weight, but the weight of the block on top. And the blocks below them have to support the weight of the materials above them. And so it turns out that each successive layer of this pyramid has to get wider to have enough surface area available to support the weight above it. So that you cannot build a pyramid that looks like a church spire. Limestone will not support this. Limestone requires some maximum slope angle that's pretty conservative. You can't build a straight tower out of limestone. It's not strong enough. What they figured out was that 52-degree angle that was used for this pyramid was too steep. The limestone was not strong enough to support the material above it at that angle. Now you're going to see this over and over and over again in construction. And here's a good example. Imagine for a moment that you have a conveyor belt. And off at the end of the conveyor belt is pouring some type of soil. It's landing on a pile. That pile of soil is going to take on a certain shape, a certain cone shape. Now, if that material is, let's say, damp clay, the walls of this pile are going to be awfully steep because damp clay is sticky. Or another way to think of it is the walls of this pile are going to be awfully steep because there's a lot of available friction between the particles of damp clay. And in fact, we call this angle, the angle of the side of the pile, friction angle. And it's determined purely by the amount of friction available in the soil. So let's consider another pile. Let's consider a pile of something like silica sand. Silica sand has very little internal friction. So silica sand might form a pile that looks more like that. It would have a much lower friction angle. And again, we could measure that angle and it'd be a good descriptor of how much friction is available in the soil. Now, I'll tell you where we run into this, or where we see it as rescuers, is people will be excavating a trench. So here's the ground, and they'll cut the wall of the trench straight down to do the work in the trench. And you can imagine that this vertical angle is much steeper than the friction angle of the soil. And so what happens is this soil will fracture along an angle equal to its friction angle, and this entire block of soil will do what we call sloughing. It will slough into the trench. Well, you can imagine that if a person's here, they're going to be crushed by this soil. Good rule of thumb for soil, it's about 3,000 pounds per cubic yard. So extremely heavy, and typically when we go to these things for rescue purposes, this is a body recovery. This is not frequently survivable when there's this type of a trench collapse. Now, in attempts to prevent that, OSHA does have some rules about operating in trenches, and one of the rules is if you're going to go into this trench, one of your options is simply to cut this soil back with excavating equipment before you enter, so that you would excavate out all of this equipment, or all of this soil here. And if you think about what you're doing, you're basically cutting the banks back below their friction angle so that the soil is safe. An alternative is a trench box, and I'll show you a picture of a trench box here momentarily. So here you see a trench box as is commonly used in construction, and again the purpose is to protect the worker. So here you can see we have some welders down there working on the pipeline, and we've secured either end of the trench with a trench box. On the far end of the trench here, they're actually using another product called sheet piling to hold back the soil. But the moral of the story here is that you have to keep these soil walls from collapsing in. Later in the course, we'll watch some videos where we see some very, very close calls with workers in the trenches that are not properly protected. Here you see diagram 1.2, the bent pyramid at Dashur. This was actually constructed in the time that the first pyramid